All right, so I'm not really going to introduce that very Fab, because everybody knows
No,
Fab.
you want this, there you go.
All right. What I wanted to just mention real quickly is you're in the software engineering process architecture and design track. There's 3 rooms, 4 tomorrow, and we're in the middle of a software test mini track. So starting before lunch and up until the next presentation, we're talking about software test. If you want to stick around for the next presentation, there's going to be a panel discussion featuring all of the different speakers in our mini track and a few other champions of software test in the community. And so, without further ado, Fabiola.
Thank you. All right. Well, I guess now we start this thing.
So, who are you?
Oh, okay. So my name is Fabiola, or you can call me Fab, as in fabulous and modest. Emphasis on the modest part. I've been doing LabVIEW since 2000, and you know that I'm a big advocate for good software engineering practices. Source code control. Who here is using source code control? Yeah, you already know that if you say no, I'm going to go and eat you up. So source code control, unit testing, BI analyzer. And why is it that I give you such a hard time about that? It's because I want people out there to recognize LabVIEW developers as serious software programmers. And we're not going to be taken seriously until we're doing software engineering practices. So, now you know why I get so passionate.
Okay, and my name is Orozco. I am a hardware engineer at Delacor. I worked for 11 years at NI doing compact radio modules. And about 3 years ago, she talked me into joining Delacor full time. So now we do hardware and software.
All right, so we're going to be publishing the content of this presentation probably next week with some notes and stuff that we discussed today. So take a picture of that and just keep checking it. It's basically going to direct to our blog post. We help teams and work on the software engineering process optimization, best practices. A lot of the things that you hear me talk at presentations at NIWeek or on our blog is what we help teams do. Most of the times it's people that are either going from a lone person to a team, or folks that have been working in LabVIEW for several years and they just realize that they're actually doing software. So we help them with software engineering practices and figuring out what tools and all that stuff. We have customers all over the world. We have 2 products in the LabVIEW Tools Network, the DQMH, which won Product of the Year in 2016, and the locking amplifier for my Rio. And then we have a set of other tools that are based on DQMH that are not on the LabVIEW Tools Network, but that we sell directly to our customers. The reason they're not on the LabVIEW Tools Network is they require a little bit extra training, but they are based on DQMH. So if you are interested in test sequencing, configuration management, stuff like that, come talk to us. All right, we are announcing this program that we're starting. We realize now that if you look at the schedule, there were a lot of sessions that said DQMH, and there's only 2 of them presented by Delacor, and I didn't even know all of the presenters. So DQMH is taking off, and we want to make sure that if you are taking if you are deciding to use the framework, that you know that you don't only rely on us, that there are other trusted advisors, other companies around the world. Wiring and Software, for example, is in Australia, Studio Bus is in Canada, and Test System Solutions and Automated Software are in the US. So we are starting that. It's also going to be on our website next week. All right.
Okay, so when I started university in engineering school, the very first thing my first engineering professor said to us the first day was, we are in the business of predicting the future. And everybody kind of laughed at them and ha ha ha, whatever, but we are. And in fact, probably everybody in this room is in the business of predicting the future. And that really happens by applying the scientific method. You come up with some hypothesis that you've worked to formulate, and then you design an experiment and execute the experiment and look at the results, and either say, yes, my future prediction was correct, or no, I royally screwed it up, let me make another prediction that hopefully works this time around. And this is going to be sort of the theme of the presentation here, how this applies to both hardware and software in many ways.
So the motivation for the presentation was that we would get together to talk about what he does with his hardware customers, doing schematic reviews, layout reviews, bill of materials, actually figuring out the specifications for their boards, what is the important things and everything. And I will be like, it sounds a lot similar to what we're doing. I really think you're doing test-driven development. And he will look at me and he's like, no, I don't do test-driven development. I'm like, yes, you do. And I'm going to submit a presentation for NIWeek where we're going to show what's the commonality.
That's great.
And then we spent weeks and weeks debating what were the commonalities. So hopefully you do agree with one of us. So we call it software test-driven development. How our engineers call it?
This is just what we do. If you want to do things right, this is how you do it.
Okay. So most of you raised your hand that you were doing hardware. So my other motivation is, why is it that you're going to be doing some of these things that we're going to discuss when it relates to hardware, but when it turns to software, it's like, so we're going to talk about that.
Okay, so when I left NI, I went to work for Analog Devices for a few years, and I was actually in a role that took me to visit a lot of customers, see what they were working on, help them be successful in whatever project. A lot of people called it sales, but it wasn't sales. I never got a commission. I wish it'd been sales. It was just sort of a traveling engineer, whatever you want to call it. And what I found is that, man, a lot of companies have a ways to go. Some of the stuff that I learned at NI and some of the stuff that I learned what not to do with these customers has sort of inspired a lot of these things. And really the message is, if you start and proceed through your development with a clear, measurable idea of what your end result should be, it is really the cheapest and most efficient and really the only real way to go about product development, and whether that be hardware or software. The goal is, before you even start doing anything, you need to know what you want to achieve in a very specific way. So, it's a great ideal. It's very easier said than done. That's why not very many people do this. So we started talking, and it turns out that it's not so different from what the software people do. Supposedly.
So a clear, measurable idea really means a complete and absolute understanding of what you're doing. So, and also the bugs, right? That you need to start with understanding that. So that it is a lofty goal, but we're going to try to achieve that. So where did we start?
So we start with getting together with our customers and deciding, okay, what do we need to do? What do you need? What do you want? And before you start designing anything or drawing any VIs, or let's put it in a piece of paper and agree of what is it that we have to do at a minimum to consider that we've achieved the goal that we're after. At NI, they used to call this green, yellow, red when I was there. A green, yellow, red form. You have your things that you must do. If you don't meet these things here, you don't have a product. It's not even worth doing. If you can get some of these things over here for free, well, great, go ahead and do them, but maybe not necessarily spend a lot of time or a lot of money doing them. And there are some things that we're going to agree up front that we're not even going to try to do, so that a few weeks or months down the road into the project where somebody walks in and, hey, wouldn't it be nice? Let's just go do 24 bits of whatever. It's like, well, no, we already agreed we're not going to do that. Unless there's a good reason to come and redefine this whole thing, let's not even bother having a half a day worth of discussions to do something like this. And if you don't do this, which, again, it's a lot easier said than done to go through all this process, you can still go design things, but what you're going to end up with is you're going to have to over-design because you don't really know what you need. Things are going to be expensive. You're going to say, hey, I need a voltage regulator. Well, how much noise? Well, I don't know. Well, okay. We can find a voltage regulator that's most likely going to meet what you need, but might not be the best one for what the system really needs.
We can find what you want, not necessarily for what you actually need. So what would be the equivalent in software?
Software requirements?
Software requirements. Yeah, it is a mythical creature, but it has been seen in the wild. They exist. How do you help your customers? And when I say customers, it can be internal to your company. How do you help your customers define what is the minimum acceptable for your software?
Well, ideally, they write it and come to you with it.
Ideally, they write it and now that it is a mythical creature. That's a dragon that I have never seen.
We just completely changed how we engage with customers on projects to be more highly iterative, so they don't have to know everything.
Yeah.
Exactly.
So a customer is not going to give you that table. No way, right? I mean, you give them this blank, and they won't even know what half of this stuff means.
So what was
So
it?
I think maybe what you're looking for is define the scope of the work.
Yeah, like the very first thing is, what is the minimum feature set that we need? And the way we get these answers, it has changed a lot. We have realized that if you spend a lot of time trying to define everything, the customer is going to throw at you what they want, not what they need. And it is our job to help them figure out what is it that they need. So some of the questions that I have come up with is when we work with startups, right? They are trying to get funding, and the way they get funding is through a demo. And when you are showing them what you're doing, because it's a startup, they're like, oh, I didn't know you could do that. Could you? Wouldn't it be great if you? And then they start going on these tangents about how the user interface is going to look like. And I'm like, no. Show me the script. And I want the 5-minute version, the 30-minute version, the 1-hour version. When somebody comes to your startup that's going to give you money, what is it that you want them to see? That's how I get it with the startups. And it has worked really well. Because I have a way of getting a check mark at the end. I do every step of the script. I'm good. And I can understand it because I have, in the history of doing this, some of the best feature requirements have been, we have to wow the end user. That was actually the requirement. So how do I know I have...
I'm a lot more easily amused than most end users.
Exactly, yeah. So most of the time I thought I was already very surprised and the customer was like, no, not wow enough. The other one is, I'll know it when I see it. Yeah. Oh, the worst one was, I'll know it when I feel it. All right. So what is your minimum test coverage will be something that you would ask if you're doing a test system, for example. What is your application critical feature? Can you define what is the one thing that your software is supposed to do? And on this one, it's important to maybe ask 2 or 3 people that are on the group, right? Because you're going to find that everybody thinks that they are asking the same thing, but they're not. When they say, I want LabVIEW code, I don't need an executable because I want to be able to tweak things. How many of you have seen that? All right. You need to define what it means to tweak things, right? Because I'm coming as a LabVIEW developer, and I'm creating DQMH, API testers, all these things so they can write code. And the more you start giving them these things, they're like, there's too many buttons. I would like to just press one button. You know, I would actually go to a window and change. So what they mean by tweaking things is they want an executable with a configurations editor where they can go and change the numbers. But they still want click once, and the demo starts, right? Or the application starts. So it is important to define what all these things are and make sure that we're on the same page. So these are just some ideas to questions. If you want to share with me some other creative ways that you have gotten to figure out and extract from the customer what they need, not what they want, I'll be happy to hear. So this is a typical scenario. Paul Morris mentioned this in his presentation because we did together an Inception deck. If you haven't seen it, it's an exercise that I recommend a lot. I have done it for different things, even for quoting projects. And one thing that I was telling James yesterday, do not skip any of the slides. There are some that are going to feel like they're fluff and that your engineers are not going to want to do. Like, for example, there's one where you design the box of your system. They are there for a reason. You start building first team building and making sure that everyone on your team is on the same page. So when you get to the what's in, what's out, they are already at least on the same page of what the objective is. If you start with what the features are in and what the out, they're going to start with their defenses high and without an agreement of where is it that we want to get to. So the very first thing is to make sure that we're all in agreement, because you might be saying, oh, we're doing software to do geometric figures. And everybody says, yes. Except one was thinking squares, the other one was thinking triangles, etc., right? So I recommend if you Google Inception deck, you're going to get to it. and it's also part of the Agile Samurai. And this is a book that Ernesto recommended to me. I should actually have Ernesto post on the here's over there on the blog post, because he reads really good books. So he gets to read 5, 6, and then he just gives me the good ones, right? All right. So what we're gonna do is gonna go through some steps of how is it that we're gonna get to this test-driven development, and what is it that we agree that was common between hardware and software. So the first thing is modeling. So determine expected outputs, determine the modules. So this is, I said it already several times, figure out what you need before you address what you want.
Okay, so this is something that happened to us in a project we did a few years ago, where we didn't go through this exercise, or actually the customer hadn't gone through this exercise, and we got hired on to help them do design reviews and sort of improve their non-working device, right? And so they said, we need a 16-bit DAC. And they said, well, okay, how good does it have to be? I said, well, I don't know, just go get a good one. We need a 16-bit DAC, because 16 bits is a lot of bits, and it ought to be good enough. We're like, okay, fine. So we found, well, actually, they had found a really good 16-bit DAC, right? It was, you know, you can't see this in the back, this is $31. They put it in and it worked, and as far as they could tell, they were ready to go, right? And then we started doing a thorough analysis of the rest of their system, and we found that this 30-bit or $30 DAC had one LSB of nonlinearity, right? It had one part in 65,000 of nonlinear error. The rest of the system had 100 LSBs of nonlinearity. So we said, well, let's go find a DAC that is a little cheaper. So we found the same DAC, same part number. You could just take one out, put the other one in, talk to it the same way, except it had 4 LSBs, right? It was 4 times worse. You wouldn't be able to tell the difference in this system. And in fact, they couldn't tell the difference. And it was a third of the price. It was $10 instead of $30. This happens really often with some of these designs that we look at. And the typical response is, well, it's only $20. I'm going to sell this thing for like $5,000, right? It's only 20 bucks. To which I say, hey, you make like $1 million a year. Just give me $20 right now.
Yep.
Just what's 20 bucks to you, right? You make a lot of money. And obviously nobody takes $20 and gives them to you. So I mean, it's the same thing. You're just throwing money down the toilet because you're skipping steps in the process.
So the equivalent, the example that I have is on software. When I ask a customer how many seconds worth of data they're willing to lose, and they always say, no, I have to have every single data point, right? And because I have to have every single data point, I have to be writing to this right away. And I have to be writing every data point. This is the easier track than trying to figure out what type of data I'm acquiring and what is the type of analysis that I want to do. So in one of the cases, I just said, okay, we're going to do that. And the hardware we were working with was a solid-state drive, and it was keeping up really well. And then they released the product, and it turned out that some of their end customers were using spinning drives. And it would take 2.5 hours after the 30-minute acquisition had finished to write everything to disk. And I was like, okay, so now we agree that writing every single point to disk is not really what you need. That's what you wanted, but that's not really what you needed. So can we look into buffering that? And it ended up being that all we needed to do was buffer 1 second worth of data, and then the thing kept up really well. So it's like, after the customer saw 2.5 hours versus losing 1 second of data, all of a sudden he was really keen on doing buffering. But this is an example of going for what you think is the best approach, or trying to buy the most expensive hardware that's going to be fitting to what you're doing, instead of trying to figure out, can I make my code more efficient so I don't have to rely on that expensive hardware. Okay? And it really boils down to understanding the problem. You have to take the time to figure out the implications of the trade-offs that you're taking, right? And that's going to be saving time and money. It seems like, oh, Fabiola, we're doing too much talk. You're having me doing an Inception deck. We're doing drawings. This is just not productive, right? I want to see running code. No, all this discussion needs to happen, and it's a lot easier to throw away a piece of a napkin or erase a whiteboard than throw away software. And the other thing too is benchmarking critical operations on a typical target really is going to save you headaches early on. If it is that you benchmark early on and performance, and you cannot improve the performance, and you really decide that, we need this, then it is okay to say the restriction is that we need to go to better hardware. But it's not okay to just do it because it's the easy answer and I want to save money on time on doing benchmarking, all right? All right, so the next step is design before you build.
Okay, and this goes back to knowing what you're going to get before you get it, right? We don't even start drawing schematics until we've sat down on a piece of paper, or it's 2018, right? There's no paper. We use MathCAD, and what we do is we try to basically predict this. We know what we want to achieve. Let's come up with a circuit. And what is this circuit going to do typically? What is it going to do in the worst case? And how are we gonna test it? Right? You can, anybody can put together one of anything and make it work. But if you're going to build 10,000 or 1,000,000 or something, you don't want to be sitting there testing them and passing or failing units based on, do they do what I wanted to do? You really want to be doing your pass-fail criteria, or on, if they put this thing together, if they put all the bits in the right place on my board, is it going to work? The only thing that can go wrong is manufacturer didn't assemble it right. If you can, by design, guarantee that your performance is going to be met, then you don't have to worry about characterizing hardware. You're just testing to see if it was built correctly.
So what's the equivalent in software? So in software is before you start going and wiring like crazy in your block diagram, which is a lot of you, right? Oh, that's a quick problem. And that's one of the things I loved about Jeff K's presentation this morning at Keynote. Like, oh, great, yeah, this guy. And then immediately I started seeing visions of my customers creating really fast spaghetti code because they can draw these sketches so much faster than when they're wiring. Sorry, I'm gonna have to. All right, so you can start putting down VIs until you get a working application. Now, working is very relative term. I have a customer that calls me probably once every 3 years when they have a bug that is really hard to solve, that they've tried everything. And every time I go into that code, I solve one problem and it's like opening a can of worms and everything starts flowing out. And it is because they don't have a good architecture. But his answer always is, but it works. I'm like, if it was working, you wouldn't be calling me every 3 years with production is halt, we need you, and I don't care how much you're going to charge me, we want you to fix it, right? To me, that's not a definition that it works. But for him, that's a definition that it works. And money-wise, he's making so much money with something that works that he doesn't see the need of refactoring. Or you could design your application first, decide what are the modules that you need to build, what are the tasks that they're going to be doing, how you're going to be testing them, and then you start deciding, okay, once I define these are my features, this is how I'm going to test them, you write the code now to pass those tests. And this is where, when I hear him talking to his customers, I'm like, okay, this is the same thing. He's trying to define first what is it that the specs and how they're going to be tested before he even starts drawing the schematic. So if you guys were designing hardware and doing this before you became LabVIEW developers, why is it that you stopped doing it when you became LabVIEW developers? Right? You were doing some math and some drawing and some schematics. Do the same thing. And then the next thing is also a great definition of, or a great benefit from unit testing is you know when you're done. And this works great when I'm working with contractors because I can tell them here are the unit tests. When these unit tests pass, you're done. There's not, oh, but I added this feature because I thought it would be great. No, if it's not part of the things that get tested, you don't spend time on that. So it makes you more efficient too. And it allows to say, this is what I'm going to do instead of trying to go, getting too creative. So reality check, does it do what I expected it to do?
Okay, so and this is where you've predicted what your design is going to do. You've built whatever you're going to build, but before you actually build anything, you want to make sure that you've designed a test plan as part of your hardware design, because it's a lot easier if before you start physically laying out a board or drawing circuits, if I have this table of specs I need to meet. Some of these specs may not be even relevant to the customer, but they're relevant to you to guarantee that your product works by design. You need to be able to test them somehow, and if you do that during the design stage, it's a lot easier to place test points, design any built-in little jigs or fixtures to go into your board than trying to add some of that stuff later. And also, the idea of a test plan is you're not going to execute this test plan to prove that the design works. You're going to execute the test plan to validate that all these assumptions and all these models that you build and all these predictions and all your math is correct. And this goes back to what I said a little earlier. If you can prove that the thing is doing what you said it was going to do, that gives you confidence that all these calculations and all this modeling you've done is correct. And so if you can predict typical behavior and you can use the same assumptions modified to predict worst case behavior, that gives you a lot of confidence that when you go build 1 million of these, they're going to fall within that worst case behavior you predicted. And of course, of course, when you start executing this test plan, I mean, some of these things aren't going to behave the way you predicted because nobody's perfect. But the key there is to understand why not, right? If something is kind of broken and you go fix it, well, it's not fixed until you understand exactly why the fix actually fixed it. And that just means that every performance parameter, every feature, even if the customer doesn't care about it, it still needs to have a test to verify it for your own completion of the design.
But one thing that when we were reviewing the presentation, we were discussing about, for example, aerospace engineers tend to love to remove tests just because the faster we test, the better, right? And cheaper. And it is very good if you understand what are the key features that you need to test. So you know how much you can remove and still be having a successful test, right? So it's going to be the same in Subwork when you get to it.
Okay. So again, if you design your test plan as part of the product design, that means when you get your boards back, they're going to be easy to test. I mean, today you may have an integrated circuit with 1,000 balls on it, right, a bulk-rate array, and there's no way to get to the stuff in the middle unless you've specifically made arrangements to pin it out, to bring it out to some fixture. If you're dealing with stuff in the higher end of frequency spectrum, well, high for me, which might not be high for some of you guys doing terahertz stuff, then you want to have little jigs where you can put your scope probe on it and have a real short ground and not basically mess up your signal in the process of testing it. Anytime you add stuff later after you got your board, you add warts to the board, and that just degrades performance, makes it hard to test. And also, if you can test it on the bench, it's going to be very likely you can test it in production easily. And so what we're trying to get is, we're trying to get to stuff like that, right? And not necessarily things that look like this over here. That is not from one of our customers. In fact, I'm still not convinced that's not Photoshop, but I mean, some of the people we've worked with in the past, I wouldn't put it past them to try to do stuff like that.
So we were trying to figure out what would be the equivalent of a word in software. So if anybody has a good idea. Christian, you had a question. You raised your hand. So.
Yeah. So you talked on the previous slide about testing things, and I was just wondering, like, I'm not really familiar with hardware testing. Like, what would be an acceptable? If I had an ADC, for example, is hooking it up to a function generator and then connecting it to a computer and reading the results, like a test that you would consider to be that kind of thing?
Well, it depends.
It depends on what is it.
I mean, I could talk for the whole day about just that question, but it depends what you expect the ADC to do. I mean, what are you, like, if you're testing linearity on an ADC, you are going to hook it up to some very, very linear source, and then you're going to read with a computer or some sort of digital device, you're going to read the codes out of the ADC, and you're going to look at, does the linearity match what I put in? And does it agree with what the datasheet says that it should be? and especially something like linearity that you can affect a lot by how you lay out the board, how you do bypassing.
And the reason for that is because linearity was the thing that you were interested in, right?
Right.
If you are interested in something else, and this in software, the way it translates is, of course, you're not going to be doing a unit testing for the add function, or you already know how to open a file, write to a file, close a file. You're probably not going to do a unit test for that. But if the feature is, I am parsing a comma separated value file that has in each column the settings for my program, that's a different thing, because there I want to validate that the columns are on the right place and that the values that I expect are in the right place. Does that make sense? So this is why we say you don't go and test everything. We had a customer, remember when he wanted to us to find a 1 volt standard, and like some of the tests that he wanted to define were for us to verify that the power supply that we were using was actually producing a volt. I was like, that's a little too much testing, because I'm trusting that the guy that sold it to me is giving me that. And it was not part of the main.
For example, if you say, ADCs typically advertised as no missing codes, right? And you can test for that on the bench to make sure you didn't just royally screw it up, right? But once you've said, yes, this design has no missing codes, you don't have to test that in manufacturing. That's a test that might take you 5 minutes. So it's a matter of deciding is my design is guaranteed by design, right? And so one of the things that we do is, once you have your test plan, it should have things like this inside, where you have a very clear description of what are you testing. There we go. What is the spec that we're trying to hit, and what are we actually expecting? And those two might not be the same. A published specification might take into account a lot of headroom for process variation, for temperature variation, many degrees of temperature variation. The stuff you're testing in the lab is going to be something different, most likely something better. And then describe what you're going to test, and describe specifically, okay, I'm gonna probe here, I'm gonna probe, I don't know, somewhere else over here as my reference point, and I expect to measure that. And if I don't, then I'm gonna go and find out why it's not behaving the way I expect it to behave.
So what's the equivalent of software?
Unit test.
Unit test. So what are the things that we're expecting on that unit test? That will be similar to this.
The inputs, what are the outputs?
What are the inputs, what are the outputs? What is it that I'm trying to test? And it needs to be very obvious for the developer, if the test fails, where to go to fix. Right? Those are the things. So what we do on software is, if we're testing to the plan, we said that here from the firewall guy, that a clear description of the test methodology, including where to probe and what to expect. So you're doing the same thing on your unit test. One way that we do it at Delacor is we use bookmarks. So for example, the example I was giving about the comma separated value file, there are going to be different VIs and different sections where I am defining what the titles of the columns are. There's another section that I'm defining what the range of the settings are. So maybe on all those VIs, I have a bookmark that says setting definition or CSV file definitions, and including that bookmark on the unit test for that. So if that unit test fails, I have notes on how to figure out what are the VIs involved beyond the one that's on the unit test, because this could have been related to something else. And two, I know what other siblings of these VI I need to go check. Because you don't want to be solving one unit test and then you run the unit test and then now you have another one that breaks. And then you run the unit test again and now it's easier. Okay, I already identified that I changed a feature of my software and it already broke this unit test. What are the other unit tests that are likely to break? And then I just double click on the bookmark manager and go to the same bookmark. Does that make sense? Yeah, so that's something we do, and the instructions on how to test it and where to test. So yes, I already said that. Good software unit test, developer can identify right away where the problem is, which is much easier if you design the code with testing in mind. So how do we define what is it and how is it that we're going to test? Well, if you're using DQMH, you better be using your API testers. And the API testers are guiding you to make sure that any new feature, any new message that you're including has at least an interactive test on it, right? The other things that you want to design before you implement the solution is whether you're going to just stay at the manual PQMH API test or if you're going to do a unit test, and whether you're okay with just that manual or you want to be able to run all of those tests automatically. Now, what happens if you add tests later? So Luis showed you that bug with all the different wires, right? I get hired sometimes to add unit tests to code that's already done that they want now to pass for FDA or for whatever regulation. Now they want to add unit tests. And I come in and the first thing I say is, that cluster-Saurus, that right there, that huge cluster, which by the way I found on the exchange, on one of the exchange points, when you actually open the little VI where it's going in, you're only using 1 or 2 elements of the cluster. So the first thing I say is, I'm sorry, I'm going to put an unbundle outside, and then I'm going to test the VI inside. I get so much pushback from people. It's like, no, you're supposed to just add unit tests, but not refactor my code. And those are the same people that are totally okay and understand that we have to order a new rev of a board if we don't have the test points in there. This is the same thing, and it's actually cheaper to add the test points here than it is to add them to the PCB board. But for whatever reason, the hardware engineer mind is okay on spending that money on the new test points, but the software mind is not. And if somebody has an answer for that, please let me know so I can use it with my customer. But this is the story that I just said. So why does it have to be different in software?
Okay. So back to the test plan in the hardware world. You know, you've done all your tests. You've written them down on a table that says, what are my tests? What do I expect? What is the worst case? What did I actually measure? And you start going through your measurements, and you see some things. For example, I expected, and this is just some examples, things that I may have seen over the last several years. I saw 0.2% or 0.4% of gain error, but I expected 0.2. And you might say, well, that's okay, the worst case is 0.5, you're good, right? It was like, well, no, because that worst case might be over 50 degrees of temperature variation. But I really expected 0.2, but I'm getting 0.4, so I gotta get to the bottom of why am I not within expected. Similarly, if I'm looking at noise and I expected 15 microvolts and I'm measuring 5, ooh, let's go have a beer because we did really good, right? It's like, well, no, but you expected 15. So maybe you're buying an amplifier that happens to be pin compatible and you can put it in, but it costs 10 times more or something. So the goal is, okay, does it do what I expected it to do? And if it doesn't, then you need to understand why. And again, we're not proving that the device works. We're proving that the behavior is what I predicted. And you can make one of anything. It's when you're trying to make a lot of them, you want to be guaranteeing things by design so that when you put all the bits together correctly, it's just going to work.
And then for software, it's the same thing, right? So we were talking again, the main goal of the unit test is not to prove that the software works. That you can prove by just hitting the wrong arrow, right? What we're doing is the unit test is a suite of experiments that prove that our hypothesis, our models, what we said was the expected behavior is working. And my favorite thing, in hardware you don't have this much because you're not changing features all the time, but you will know if you break it when you add new features. This is why we're doing unit tests, okay? So that just goes back to, again, understanding what is it that I expect and then having an automatic way of testing it. Or to prove that your hypotheses were wrong so you can go back and fix them. The main thing here is what we were saying is even if it looks better, you need to understand why it looks better. If it doesn't work, you need to understand why it doesn't work. Get to the root. This is the joke that you said.
Yeah, we're kind of running behind here, so that's the joke. You know, in software it's milliseconds, in hardware you press the run arrow and it's 2 weeks and $10,000. So don't get to run it very often. So other things we've learned along the way. We've talked about expectations, I guess, enough for today. Some things we've learned is that you can do quick prototypes. You can, in the process of predicting performance and really understanding things, you can use simulation. I'm not sure if some of you guys use LT-Spice or some other spice of some sort. That can only take you so far. There are so many things that you can simulate. There's some other things that either you're not putting in the model or you didn't know about, where just making a little board can give you a lot of insight. And we want to be careful. This doesn't mean you make a board and you characterize it and you measure it. And hey, I measured a volt here. That means every one of these boards I make is going to be a volt. It's really, I built this thing, and again, I said I wasn't going to talk about expectations anymore, but I built this thing and it works the way I expected it to. So that means I can put that circuit on my board because I understand it. Or hey, this doesn't quite do what I thought it would do. Let me poke at it and measure everything and make whatever changes until I understand it really well, and then I can go put it on the board, on the main board. And you can spend a couple $100 in 2 or 3 days and have some of this instead of waiting till you have your whole design complete, and now $5,000 later you find out you didn't understand some little piece and then it doesn't work.
So when we were preparing the presentations, I was really trying to get to the modules part. And he was like, well, but it's obvious, right? You do prototypes. I'm like, yeah, but I don't want the obvious. I really want to stay the obvious because I want to find the analogy with software. So the analogy with software is you can prototype subsections of your application in isolation. You're doing your API testers or your little testers where you are just testing one part of the software. And it's the same thing, it's really quick, right? I have heard people that use DQMH that say, well, I started to get nervous because I'm used to seeing the top level UI ready pretty early on. And now with this approach, I have all these API testers that are working, but how long is going to take me to put them together? And then they get really excited when it goes really fast because all the individual pieces work. When they put it together, it just works. Then this is one of the advantages of the API tester. It needs to work, it needs to be clear, but it doesn't need to be pretty, right? You're just using it as a quick prototype. The other thing is you invest days now on doing that API tester. You save weeks later. And as some of you guys have seen, if you use DQMH, you can use the API tester to debug later.
And then we run into customers that say, hey, we should have done this yesterday. We don't have time for this test plan nonsense. We're just going to build it and test it. Like, okay, but
That's not it, sorry.
too far. The first question that comes up is, how do you know when you're done? How do you know that it works? You plugged it in, and I guess it didn't catch on fire, so it's probably working.
But it runs?
But it runs. Or you plugged it in, and data came out, right? And you get like ones and zeros coming out. That must mean it's working. And I have some more detailed examples of that here. But more importantly, how do you know when you're done, right? You can be testing something for 6 months because you just keep poking at it, but without a plan, it's hard to work efficiently. So in real life, some things that we've actually run into and helped people fix. A design where 60% of the cost was in components that were not required. Literally, within the board, you erase those things from the schematic and replace them by things like resistors and wires. And
It didn't make any difference.
it didn't make any difference because people had just thrown things at it because nobody really spent the time to really design something. Or we had some device that was acquiring data from a light sensor, and it was working. Data was getting across, and they were seeing stuff on the screen. But when we were done, the noise was 10x worse than it should have been because a little stage in the circuit was oscillating, just enough to cause all this noise that they couldn't really tell it was just oscillations. But it worked, right? It was, as far as they knew, it worked until maybe a year down the road when they tried to actually compare it against some benchmark that they had to meet to get their funding, and then they would have realized that it didn't work. And then finally, some other circuit had a frequency response that was only half of what it was supposed to be because nobody had ever bothered to put a scope on it and check it. It worked. You got data, you got things come across. It just, it was only half as good as it could have been.
A good example for this on software is the magic delay fairies. right? Where people put a wait 10 milliseconds and then they upgrade LabVIEW and the wait no longer works. So same thing on software. No, we're behind. We are behind schedule. I don't have any time for those silly API testers. What are you doing, Fabiola? You're spending way too much time on that. Same thing. How do I know that it works? How can I? It's just the fact that your runs is not enough because you press buttons and they do what they're supposed to do. Is that enough? We really need to know what's going to happen in case of an error. Am I handling my error cases right? What happens if things on the VI break? And another thing is when you have unit tests and you know how long those unit tests take, you can actually say how long it's going to take me to, like, you have a progress, right? A progress bar. Let's say you start with 100 unit tests and the customer says, how far are you from being completed? Well, you can say I have 10 unit tests that pass. So I'm obviously at 10%, right? So it becomes kind of a metric. It's not linear because sometimes it starts to go a little faster as you go through. So in real life, the customer, this is the typical, they complain about why are you spending time on API testers? And then they needed to replicate a new system. And they get new motors and they get new syringes and they get all this equipment and the customer calls me and he says, how do I go about this? And I'm like, well, remember those API testers that you kept complaining about me spending time on
I didn't
that?
want to pay for it.
And you didn't want to pay for? You run each one of those. As you are wiring the motors, you run the API tester for the motors. When you're done wiring the syringes, you run the API tester for the syringes. They had budgeted a week for replicating the system. They were done in a day. And that's when their boss was like, when are you bringing that Fabiola back? Yeah, it's like, but we have 2 more projects. So and then the application just worked. So that's just, yeah. All right, my favorite.
Okay, so other things we've learned along the way that seem fairly obvious, and except they weren't obvious back then. Every product you make must have blinky lights. I mean, yeah, that's it. Somebody calls you, hey, it don't work. And you don't want to say, did you plug it in? Because that makes them sound like an idiot. But you say, hey, is the light on? Is it blinking? Is it blinking 5 times or whatever?
Is it red? Is it orange?
Yeah. So I mean, that's really just the first step in debugging when you're not there, which is for us, it happens. I mean, we don't have local customers. Everybody is out of playing right away. So.
So it's the same thing on software. So we do, for example, if you're using BQMH modules, we might have somewhere, it's either in a hidden window or on the top level, some little LEDs that show if all the BQMH modules are running. Then if you have a heart rate, it can also tell you when the typical complaint from the customer is the application hang. You can ask them, is the LED on the top right blinking? So if it's blinking, you know that the application did not hang. There's something else, it's probably doing something else. So that's and I love, in Spanish, by the way, lights, it's poquitos, little lights, so I love poquitos.
So it sounds funny in English.
Yeah, it sounds funny when I say it.
Okay, so
So
don't plan on shipping Rev A. A lot of companies, encourage their engineers. Encourage their engineers to, hey, if you ship Rev A, that means you're a really good engineer. It's like, well, really, if you ship Rev A, you're not innovating enough. You're not, I mean, you might be like changing a connector on the board or something from some other variant, or you're taking too long, right? Rev A is really your chance to try stuff that is new, unproven, to really innovate. They make real good proof of concepts. Also, because it's a Rev A, a bit of a secret is you can take some shortcuts. Some of the stuff we've talked about, like, well, anybody can build one. You got to do all this stuff if you want to build 1,000,000. It's like, well, you're not going to build 1,000,000 Rev A's. You're going to build a couple. So if you need to get funding in 2 weeks or you run out of money in your company, you can take some shortcuts on Rev A to say, hey, yeah, we got one to work. We can now, give me some money, and we'll go and do another version that really works, and we can make a lot of them. But you have to have that discipline to go back and go through this process on Rev B, not just say, well, we got this one to work, the next ones are going to work too.
Okay, so in software, don't use duct tape to take that proof of concept that you did and then create a spaghetti code around it, right? Proof of concept should be as a reference to go back to, as something that you run back to make sure that that whatever you were building still works. do not make it the heart of your application. I have so many stories about this one, and it's equally bad to have this than to have this. Right? On the other one, it was obvious that we were doing something wrong because it was a spaghetti. What has happened too is somebody creates the spaghetti and then they take a lovely DQMH module and they put their spaghetti mess in there. That's equally bad, all right? So, and it is okay to do a proof of concept, to take some shortcuts of all the stuff that we said that to do. Maybe you don't want to do it on the proof of concept, but then throw it away or save it separately and start doing things right. All right. Do not reinvent the wheel.
Yeah, so we apply this in hardware.
Oh, I went too fast.
Too fast.
Sorry.
Okay, so you've spent all this time validating stuff and making test plans and making sure you understand and that things behave the way you expect. Like, oh, great. There's some things you're going to be using again later, so save them as reference designs. They can save you time. You know this particular layout works great, and every time this is a little example of a 5 to 3.3 volt power supply and great efficiency, great noise. We'll just use it again. And you can get reference designs from vendors, but you have to be very careful because the goal of the vendor is to showcase their part and to sell their part. That doesn't mean that their reference design has your best interest in mind and that it is going to have the robustness requirements or maybe the temperature performance that you need. They're going to pick all the components around their part to make their part look good, which probably means they're going to be expensive. You may not need that. So vendor reference designs are great, but you really have to understand what they're doing before you just take them as is.
By the way, Luis now uses source code control to save those schematics and the reference designs. Just, yeah.
They don't feed me if I don't.
Okay, so in LabVIEW, what is the reuse code that we have is project templates. And I've heard people say, oh, Fabiola, come on, nobody uses project templates. We do. At Developer, we have project templates, so we're not reinventing the wheel every time. There is also a feature that a lot of people are not aware of. DQMH ships with a singleton and a clonable, but you can create your own DQMH templates. So if you have a template that, like in those examples I have, for example, a test sequencer test, or a configuration editor, or a serial manager, those are things that we have. If we are building it again for a new customer, before we build it for the new customer, we create a template.
Wait. Or if you have the hardware guy trying to write LabVIEW code, not that ever happens. I can go here and say, hey, I want a DTS test. And click, and all of a sudden I have all this LabVIEW code that there's no way in the world that I could ever write by myself. And just in a little bit of section say, okay, acquire, do some processing, load to file.
And he has all the bookmarks.
And now the LabVIEW, the hardware guy can write LabVIEw.
Exactly. And he builds. All right. So reference design portal. I don't know if you guys are aware of this. It's it used to be only systems engineering designs. I'm very happy that one of the first external designs that they had was the DQMH. Now there's other external designs. Go there, but go with what we said earlier. Right? It's reference designs by vendors that are including the DQMH. We are showcasing what we think is important to us. It's a reference design, it's a springboard. Do not expect it to do everything you need. It's there for you to change. And that's, I don't know, Peter, but it's a headache, right? Because some people call with complaints and bugs and stuff, and it's like, it's not a bug. It's just a feature that you don't need. But don't reinvent the wheel, go and check. All right, so for test-driven development with DQMH, what I suggest is you go to the documentation, and I have, as usual, videos, and again, you can slow them down. There's a video on how to create unit tests. You just go to Tools, Data Core, DQMH, add a new unit test. And there's 3 videos. There's one how to do it with JKI, BI tester, one how to do it with unit test framework, one for a custom. And then there's a 8-minute tutorial on how you would do test-driven development if you are using DQMH. So it will guide you through a whole implementation of one thing. So I'm going to skip that unless we have time at the end, which I don't think we're going to have. So, all right. So this table was painful. So I hope you appreciate it. You want to do it or I do it?
You do.
It was painful to put together because even after we had done all that, Luis still said that he didn't do test-driven design. So I don't know if he's convinced now. Yeah. All right. So what we did is I put in one column all the things that hardware guys do, and then on the other one, what's the equivalent in software test-driven development. So I think the important thing is on both sides, we define a goal. On the software side, we define the expected outcome. We design an application and test first. That means drawing on paper, deciding what are the unit tests, what are the critical parts of our code. We implement the test first. We verify that that test fails. I had an engineer that used to work for me that would create all his unit tests passing from the beginning without first implementing code. That kind of defeats the purpose, so make sure it fails. Then you implement the code to make it pass, and then you verify that it passes. And the equivalent, the hardware side, is you design your circuit and test plan to prove performance. You design your PCB with testability in mind. You execute the test plan. You compare your test results, and then you work to understand anything and fix any dependencies. So I hope that some of you guys that come from hardware background, this helps you to understand what is it that we're trying to do when we're doing unit testing.
And you said that if I agreed or I didn't agree. The one thing that our friend Steve Watts reminded us is, this business about predicting the future and software versus hardware. In the end, engineering is engineering. You're gonna make a prediction, and then you're gonna design something to meet that prediction,
And
regardless.
we are in the business of predicting.
We are in the business of predicting the future.
In the case of unit tests and all those things, a prototype would be unit tests at the BI level. A test fixture might be on software test-driven development doing the DQMH unit test suite, for example. The equivalent to an evaluation board would be the API tester. If you're having problems with a chip or on a part of your board, you go to the evaluation board to isolate it. If you're having problems on your software, you go to the DQMH API tester to isolate it. Right? And then, so this is what I just said, right? If you have a bug, don't blame the parts. Try to understand first. And this is an advantage when you have so many tests to begin with. Anytime you have a bug, you can go back. And I think, James, you posted, I think last week or 2 weeks ago on Twitter, that you found a bug, and he was like, and that's when I realized I should have created unit tests, right? I should have created them. Oh, and the sample reference designs. And Richard Feynman said, the first principle is that you must not fool yourself, and you are the easiest person to fool. So if you are not designing with test in mind, and you are writing all your code and then clicking the wrong arrow, you might say, oh yeah, 2 + 2 is 5. Yeah, great, and you just go on. But if you had written down, I expect to see a 4, and then you see a 5, they were like, oh, wait a second, what did I miss, right? So that's the main thing. I think that's the reason why I do unit tests. It's because I know I can fool myself. But if I tell the computer what is it that I expect, the computer will tell me if I implemented it right or not. All right, a little plug for GDefcon. Is an independent LabVIEW graphical programming conference in Cambridge, UK, 4th and 5th of September. If you are interested in attending, go to gdefcon.org or com.
Raise your hand, James. Talk to that guy.
And then if you register, they already sold out on the first set of tickets. They had to change the venue. So the next set of tickets are probably going to go really fast. So if you're interested in going, they're probably going on sale on early next week. So just check that. That's where we're going to put the material. Make sure you take your survey. Questions? Are there any questions?
So, when you talk about planning the tests, etc., is that putting down code, or is that specifying a high level, or kind of when do you know what I mean?
Yeah, so we don't have a formal test plan like he does, right? Like he had a whole thing with, what we do is we put down code for each unit test. If you chose that you were going to be using unit test framework, it's creating the LV test. If you chose to do JKI, it's creating the JKI class, the VI tester class, and all the individual test cases, right? If you're using DQMH, and this is what I show on the video, is your first step now is going to be you create a request, and I used to tell you go immediately to the API tester and to the code to implement the code. Now there's going to be a third step there, which is going to be go to DQMH develop or create the unit test and implement the unit test first, then go to the API tester, then finally go to implementing the code. That's how you are ensuring that you have the automated test implemented, the manual test implemented before you actually implemented the code. Does that make sense? Yeah? Was this useful, guys?
Yes.
Yeah?
Interesting.
Okay, it's just, this is something that I had in my head every time I was doing unit testing, because I find it really hard, and I don't understand why is it that it's harder for us, that we come from hardware, mechanical, things that we can touch. I would expect that it would be more natural for us, but it tends to be more natural for computer scientists, or maybe they struggle too, I don't know. But I hope that this idea of seeing your VIs as part of a PCB board or as part of a mechanical system will make it more obvious or make more sense why we do unit testing. Any other questions?
So, if you wanted to learn good software principles, there are quite a lot of kind of resources online, both for LabVIEW and not for LabVIEw, that you can look at. What would you recommend as good things to look at if you wanted to get better at hardware design?
Oh, that's a question for the hardware guy. Okay.
So Delacorte does consulting services?
The Delacorte do consulting services I can afford with like $100 or $200.
There are services for every budget. They might be little consulting services. But seriously, no, there are not very many resources that I found. I mean, a lot of the things that I talked about here, and a lot of the things I learned them either while working at NI, or at Analog Devices, or just watching people do just terrible things and suffer for it. And I mean, I've done my own share of suffering, right?
Having the blinky lights, even though we say that you need to have blinky lights, we have forgotten.
And I mean, there are books and papers on like design for test and design for manufacturing, and I mean, a lot of that stuff is really aimed at like highly regulated industries. And to be honest, it's hard to like read those long, dry manuals and specs and like apply them to real life. I think when you leave here, as long as you remember the one thing is, I need to know what to expect, and then when I go test it, it has to behave the way I expected it to, and if it doesn't, I need to find out why. I mean, that's really all there is to it.
I think what Chris is saying is he wants to see videos from Delacorte and blog posts on hardware.
That's exactly what I was looking for. I know that Fabiola has videos. Do you have any?
I have no videos.
Are you going to do any videos?
Probably not.
We'll talk. Any other questions?
Hardware guys, they don't let us have very
One
often.
thing that he brought up, you know, a lot of times we focus on, you know, we expect a certain behavior, and we focus on if it's worse, then we fix it.
Yes.
But he pointed out, if it's better than what you expected,
That's
go
bad too.
after it again,
Yeah,
because maybe there's something else going on.
Right,
there.
you need to know why it's better.
Right.
I mean, it's not just that you're lucky, something happened there.
We were doing performance improvement for Subwork last week. We went to visit a customer in Colorado. I was very excited that I was able to go down from 250 milliseconds to 10 microseconds. But on one of those, we got 1 microsecond. And I'm like, what did I do? And it turned out the loop was running 0 times. so the 1 microsecond was that the loop was...
Wasn't doing what it's
Yeah, and it was that. It was like, this is, okay, I'm good, but I'm not that good.
Yeah, if you test an ADC and it's got like all zeros on the output, and you measure noise, it's going to be 0 noise, right?
But yeah, it is important, and that's one to keep in mind. And also in the unit testing world applies to not because the unit test pass means that everything is good. It is a good indicator, but you never want to say, well, there's not a bug because the unit test passed. Any other questions? No? All right, there's going to be There's a new badge on the QMH. I understand this session doesn't really give you a lot of information for the DQMH badge. I think the only thing that would apply for is the new tool for the unit testing. Tomorrow is Thursday?
Tomorrow is Thursday.
Yeah, tomorrow the first session, so please, I know you're going to be hungover, but if you want to hear more about tips and tricks for DQMH, that's going to be at, what time do we start tomorrow?
It's the first session, isn't it?
Yeah, 9:45. So I'm going to be doing tips and tricks on DQMH. It's going to be going a little bit more advanced than the typical just create a DQMH module. But if you are doing DQMH, I recommend it. And if you want to take the DQMH badge, that one is going to have some tips for obtaining the DQMH badge. All right? Okay. Thank you, guys.